Okay, good day. This is dual enrollment calculus. I am Mr. McCully, and this is the lesson for what we're going to call section 2.6b, and it's going to start doing some transcendental derivatives. And it's essentially what we're going to do today is we're kind of picking up all of the little extra topics that are covered on the midterm exam. And so they have to do these particular transcendental functions, and a transcendental function is a non-polynomial function. Um, They're going to use these properties of natural logarithmic functions. We're going to talk about the definition of the number e, as we've already talked about, so we're going to go over that pretty quick. And then we're going to find derivatives of functions involving the natural logarithmic function, general logarithmic functions, and exponential functions. And so just some quick review from Algebra 2. And again, I'm going to go over this real quick, but if you have any questions over any of this stuff, we can talk about it in class. But the ln of 1 is 0. The ln of a plus b, or a, excuse me, start over. The ln of the product of two functions a and b are equal to the sum of the individual logarithms. And then the ln of a to the n, I can bring that n down in front and make it n ln a. And then if I have a quotient of two functions and I'm taking the natural logarithm of that, I can separate it into the difference of the logarithm of the top function minus the logarithm of the bottom function. And these can be used to simplify before you differentiate. I'll get into that a little bit later. Last year we defined the natural number e in terms of a limit. And we said if you take this expression and let x get large without bounds, you'll get closer and closer to e. And we did that with a little graphing calculator activity. And you guys can do that. We can talk about that in class as well. But they are going to define it in calculus in terms of an integral. And so the ln of x is going to be defined as 1, the integral from 1 to x of 1 over t dt. Now this notation is new and we'll be learning it in the second half. But what it allows us to do is to say that the derivative of ln of x is just going to be 1 over x. And here we have an instance of the chain rule where we say if we take the derivative of an expression with respect to x, then that's going to be 1 over that expression times the derivative of that expression. And the way that that works is here I have the ln of an expression, and so if I want to find dy over dx, then I am going to use this property. It's going to be 1 over the expression left alone times the derivative of that expression. So I get 1 over the expression left alone, x squared plus x, times the derivative of that expression, 2x plus 1. Now we should finish this out by combining it and making it 2x plus 1 all over x squared plus x, and we'll put a box around that. That is our derivative. All right. Now, again, just reviewing, these properties here are now useful. We learned them in Algebra 2, and I said it was just a good time to introduce them. But now they become useful because now we can stop having a chain that needs a product or have a chain that needs a quotient rule in there together, and we can separate them and make the derivative a little bit easier. So an example of that, here we have the ln of this quotient. And so if I use the rule that we talked about in the first slide, this chain rule slide, I would have 1 over a fraction times the derivative of a fraction that would need the quotient rule put on it. And that would be kind of a pain in the rear end. So what we're going to do is we're going to rewrite using the property, the ln of a over b equals the ln of a minus the ln of b. And so before I get started, I'm going to go y equals the ln of x squared plus 2 minus the ln of x. And so now the derivative of that thing becomes a lot easier. I don't have to do 1 over a fraction times the quotient rule here. I can go The derivative of this will be 1 over the expression left alone times the derivative of the expression, which would just be 2x, minus, now the derivative of ln x, this isn't an expression, we just go 1 over x, and we can finish that one off by rewriting 2x over x squared plus 2. This fraction cannot be reduced because there's no common factors, minus 1 over x, and we're just going to leave this as is. I could probably simplify and make it into a single fraction, but this is fairly useful as is, and if I was just trying to evaluate a fraction, or excuse me, evaluate a derivative at a given point, this would be just fine. So we're going to leave it and we're going to move on. All right, the derivative of the natural exponential function, the derivative of e to the x is e to the x, which is kind of a funky thing, but I'm going to show you why that works. And the derivative of e to the u is going to be e to the u times the derivative of e to the u. And again, this is an example of a chain rule. So real quick, why we're going to use the fact that we're going to take the derivative of both sides, and we're going to try and prove why the derivative of e to the x is e to the x. And so I'm going to start with this ln of e to the x is equal to x. And I could simplify this side already because it is just x. But I'm going to take the derivative of both sides here. All right. And so remember, the derivative of ln of u is 1 over u. So in this case, it would be e to the x left alone times the derivative with respect to x of whatever that u is. In this case, it's e to the x. And so we've completed the left-hand side, and then the derivative of x is just 1. And so I can simplify this and I can take this e to the x on the bottom and multiply both sides. By e to the x, and I'll have the derivative with respect to x of e to the x equaling to e to the x, which is kind of crazy. Some differentiation rules for functions other than base e, and these can be found in your book. I would suggest that you kind of commit them to memory. The derivative of a to the x is the ln of a times a to the x. And an instance of the chain rule where you have an expression in the exponent, the derivative of a to the u is the ln of a times a to the u times the derivative of whatever that expression is. And then the derivative of any logarithm of any base times x will be 1 over the ln of a times x. And then the derivative of a for some expression u will be 1 over the ln of a times that expression u times the derivative of whatever that expression is, and this u has to stay on the bottom. So let's do an example or two that involves that. And so here we have a product, and I like reviewing product rules because that seems to be one that people tend to forget. So if I want to find the first derivative of this thing, I'm going to take the derivative of the first expression. And this is my first expression, 3x, and my second expression here will be 2 to the 2x. And so I take the derivative of the first, which would be just 3, times, I leave the second function alone, so 2 to the 2x, plus I leave the first function alone, so 3x, times the derivative of 2 to the 2x. Okay, so which rule am I using here? I'm actually using this second rule here because I have a exponential with an expression. So since it's 2 to the 2x, I'm going to say the ln of 2, and then it's going to be 2 to the 2x times the derivative of that 2x. So it's going to be the ln of 2 times 2 to the 2x times the derivative of 2x, which would just be 2. Now, I can't really simplify this part here, and please do not make this, and I see this simple mistake over and over. Kids will write this as 6 to the 2x, and then you're breaking the order of operations. You're doing multiplication before you do exponents, and you're not allowed to do that. So we're going to leave that alone like that. I can move this 2 over to here and because it's all multiplication, so I can reorder. So 3x times 2 is going to be 6x. I'm going to move this 2 to the 2x here out front so it doesn't get confused of being inside the logarithm, ln of 2, and we're just going to leave it like that. And that's our derivative for that particular one. All right, our last one here is going to be find the derivative of this following. So I've got log base 3, and so I'm going to use this rule here where it's a log of a base that I don't know. So it's going to be 1 over the ln of the base, and that's going to be multiplied by the function left alone, and then I'm going to multiply that whole thing by the derivative of what that is. So my base is 3, so g prime of this thing is going to be 1 over the ln of that 3, and that's going to be, we're going to leave that alone like that, times the derivative of this expression right here left alone, so x to the 4 plus 6x, times now the derivative of that expression, so 4x to the third plus 6, and we're going to rewrite and combine that, so I have 4x to the third plus 6 all over the ln of 3 times x to the fourth plus 6x, and that is the answer. All right, so we have come to the end of the first half of calculus, and so we'll end it with a Star Wars fun fact of the day. Zeb Aurelios is a character from Star Wars Rebels, a fun little animated show that was on Cartoon Network or Disney XD or something like that. I don't know. But anyway, what's cool about him is they actually recycled a design from Ralph McQuarrie's original Star Wars artwork back in the 1970s. It was one of the first designs for the character of Chewbacca that they eventually threw out and went with a more hairy guy with a bandolier strap. All right, well, that's all I got for today, folks. I will see you in class. Have a good day. Bye.